Kind greetings to you all. So we continue with series of sessions on carbonyl compounds. And previously, we had gone through this. That is confirmatory tests for carbonyl compounds. How Brady's reagent is used. And I was saying that it is used to confirm for the presence of carbonyl functional group within carbonyl compounds. So therefore, once it is treated with other compounds, that lack a carbonyl functional group, nothing will be observed. So there is this very simple question, quick one, which you can think about. Here we have some compounds. Name the substance, name the reagent that can be used to distinguish between the members of these pairs. So you realize that here we have a carbonyl compound and a hydrocarbon. Then here we have a carbonyl compound and the phenol. So it is easy to see that. From what we have discussed earlier on, it's easy to see that we can employ this. We can employ that. Now, applying that reagent, methanol shows nothing. No, sorry. Methanol is made up of the carbonyl functional group, so we shall have a positive test. I'll have a positive test. I'll have a positive test. Then for the hydrocarbon CH4, lacks the carbonyl functional group, no reaction. Then for party B, still, the reagent employed is the same. And in this case, our carbonyl compound is phenylthanone. Phenylthanone, the one that gives a positive test. Then phenol, with phenol, no reaction. As simple as that. So you see how it is applied. That's why I was saying that you shouldn't forget that versatile reagent. So I want to conclude with the two examples. I think one example will be enough. Yeah, I think I've done enough of this. Maybe now with phenylhydrazine. I will conclude with the phenylhydrazine. Then I give you some simple questions to try out. I think I've left some easy examples, some easy questions here. For this case too, I don't see questions which I have left behind. I have left none. So maybe I work out one. Yeah, you see these questions were previously left for the other first case which we are exploring. But for the second case, haven't left questions. So these are more examples on case 2. More examples on case 2. So in this case, we have cyclohexanone with the phenylhydrazine. So we repeat the same steps. The pathway starts with the protonation. Protonation of the hydrogen ion, which is electron deficient. But here we have lone pairs of electrons that can be donated to the proton. Therefore, once we donate to the proton adds to oxygen, so that we have oxygen is having a plus because it has donated electrons to hydrogen, and moreover it has excess bonds. Therefore, we need to donate it. We need to donate electrons to it. We donate electrons to it as a way of giving it electrons and also as a way of using the bonds on it. Now, once we give it electrons, the carbon at this corner becomes electron deficient, but NH2 is electron rich. There are lone pairs of electrons on this nitrogen that can be donated electron deficient oxygen, like that. So that this is what we are having. So therefore, we shall obtain this is now a single bond with the OH. It is a single bond because the bonds were reduced by giving oxygen electrons. Now this carbon here, the carbon atom here, is being bonded with N. That N carries a plus. Why? It has donated. That N also carries a hydrogen, carries another hydrogen, It also bonds with another NH, but this N here is attached to a benzene ring, like that. So the nitrogen has a plus, moreover it has excess bonds, therefore we give it electrons by reducing those bonds from one of the appending hydrogens from it. Therefore, once we give it electrons, the hydrogen becomes electron deficient. It has to shift to where we have electrons. So it will have to come here up, where we have lone pairs of electrons on oxygen. So have it shifting. We are having it shifting to that oxygen. So this is hydrogen shift. That results in formation of the following. These are now two hydrogens. Oxygen has a plus because it donated electrons to hydrogen. Then we still have a bond with N, H, NH. And the N, the other N is carrying a phenyl group. Oxygen up has a plus, so it is electron deficient. Moreover, it has excess bonds. Therefore, we reduce on those bonds by giving electrons to oxygen. Using those electrons in this bond here, so we donate oxygen. As a result, a water molecule is lost. However, in the process of giving oxygen electrons, the carbon here, remember, where we are taking electrons from is a covalent bond formed as a result of oxygen contributing and carbon contributing. Now I am taking all those electrons and I am donating them to oxygen, meaning that carbon is going to be left with a plus. So we give it electrons using the lone pairs on this nitrogen. Like that. So as a result, there is loss of water molecule H2O as we form the following. This is now a double bond with the N that has a plus. N carries H. It also carries another N and the H. This N here additionally carries a phenyl group. Yeah. So the N up is electron deficient. We give it electrons like that. Now, once we donate electrons to it, a proton is lost, meaning that originally it was not participating in the reaction. It was serving certain purposes. N, NH, and the phenyl group here. Hope you still remember the name, cyclohexanone. The name is cyclohexanone phenylhydrazone. So we have this with NH. There's a phenyl group there. Plus H2O. The name is cyclohexanone. 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 Phenyl hydrazone. I believe that I have worked out enough examples. Finally, let me conclude with this one here. Another quick one. I use what? I think I have explored hydroxylamine. I have explored phenylhydrazine has been used. Then Brady's reagent has been applied here. Hydrazine was used. Maybe hydroxylamine. Let me finalize with hydroxylamine. Hydroxylamine. I take which example of a carbonyl compound? I can take an example of CH3. CHO. OH. Reacting with hydroxylamine in presence of hydrogen ions. That. The pathway does not differ much from the pathways which we have seen. They are the same reaction mechanisms, reaction pathways. They do not change a lot. So in presence of a proton, we start with protonation. We expose the site. We expose the site very well. So I expose the site. In this case, it is the carbon to oxygen, double bond, hydrogen. So we start with the protonation. In the presence of a catalyst, the hydrogen ion is electron deficient, and there are lone pairs of electrons on oxygen that can be donated to that catalyst, that proton. Therefore, as a result, we form the following. OH, then C. This is a double bond with the O that has donated, therefore has a plus. That O additionally carries hydrogen. Like that. Then the C also carries a hydrogen here. Like that. So the O has a plus, so it is electron deficient. Moreover, it has excess bonds. So we reduce them by picking electrons from this double bond because it is where we have too much electrons. Yeah. You may ask, why don't we reduce those bonds by using this carbon using this bond up here, the carbon, this one which I am trying to make thick, that one there. We don't use that. Why? Simply because down here we have a double bond. A double bond is having a higher electron density as compared to electrons which are present in that single bond. And moreover, if we break that single bond, still we go back to where we are coming from. So there is nothing Yes, I'll be doing nothing new. Yes, nothing new. So the carbon here becomes electron deficient. The derivative of ammonia is electron rich. So I donate. As a result, what do I form? I obtain the following. I have CH3, CH, OH, C with OH. Then I'm bonding. This also carries hydrogen. I am bonding it with N that has donated. Therefore, this N has a plus. Carries hydrogen, another hydrogen, OH, like that. N is electron deficient. Therefore, I give it electrons by breaking this nitrogen-hydrogen bond, which is where we have hydrogen appending from nitrogen. So we reduce on the excess bonds on nitrogen by giving nitrogen electrons from one of the bonds appending from it. So once we do that, this arrow has to reach, has to point there. Then the hydrogen now also becomes electron deficient. It will have to shift to this oxygen here, the oxygen here, which has lone pairs of electrons. So we have lone pairs of electrons there. Therefore, it goes that, so that we have a hydrogen shift. Resulting in formation of CH3, CH, OH, C, OH. These are now two hydrogens. Oxygen donated, therefore has a plus. This carbon carries a hydrogen. This is now a double bond with the N that has donated. No, with N to which we have donated electrons. So we have our N carrying H, carries H, and the OH. Of that is what I'm having. No. I think this is wrong. Sorry. This is not correct. This is not correct. This is not correct. It's not correct. So that's what I'm having. The hydrogen goes to the oxygen up, so that oxygen, it's like we are saying that the lone pairs of electrons on this oxygen have been donated. The lone pairs of electrons here have been donated to that hydrogen. That's why that hydrogen shifts to that oxygen, because we have lone pairs of electrons there. So as a result, once it goes there, what do we have? Now oxygen is carrying two hydrogens, and it is having a plus because it has donated its electrons to that hydrogen, which has shifted to it. Therefore, this is still a single bond with N, H, and OH. So the oxygen up is having a plus. Moreover, it has excess electrons. Therefore, no, it has excess bonds. It is electron deficient and it has excess bonds. Therefore, we reduce on those bonds by donating electrons to oxygen that has a plus. Once we donate electrons to that oxygen that has a plus, the carbon down becomes electron deficient, and there are lone pairs of electrons on the nitrogen atom that can be donated to that carbon. As a result, what do we have? We have loss of water molecule, as we form CH3, CH, OH, CH. This is a double bond with N, which has a plus. That N carries a hydrogen, and the OH. Like that. So nitrogen is electron deficient. You see, it has a plus. Moreover, it has excess bonds. Therefore, reduce on those bonds by donating electrons to nitrogen. So a proton is lost minus a hydrogen ion, resulting in formation of CH3, CH, OH, CH. This is a double bond, NOH, like that. So I complete my reaction here. Equation. CH, like that. So I believe that I've worked out several examples. I think I should leave some of you questions for you to hustle out. So you try out these simple stuffs. You try out those simple questions, but it is important to note that, let me emphasize this as I am ending this session to have a short break. It is important to note that dilute sulfuric acid, in this case, serves as a catalyst. Dilute sulfuric acid in this case serves as a catalyst. Catalyst which protonates the carbonyl compound, compound serves as a catalyst which protonates the carbonyl compound, inducing using adverse polarity of the carbon to oxygen double bond. We have seen this separately. Serves as a catalyst which protonates the carbonyl compound. This case serves as a catalyst which protonates the carbonyl compound, inducing advance. This is not induces. Using, sorry. Using inducing more polarity, or I am calling it advanced polarity of the carbon oxygen double bond.